Hi, Vidya.
Hi, Prof. Naresh. How are you?
Not too bad, not too bad. Thanks.
All right. Um, we are still waiting.
Yes, still a
Yeah,
couple of minutes
still,
to go.
yeah. Hope you don't mind.
No problem, no problem at all. Um, Today we had a bit of sunshine in Sydney.
Oh,
It's been raining for last week.
is it heavy rain?
Um, I think just annoyingly mild rain.
Is it windy?
Yeah, I think a couple of days ago was quite windy, but now it's calmed down a bit. Yeah.
Yeah, it's supposed to be hot summer.
All right. Yeah, that's right. Hasn't quite started yet.
Oh yeah. November.
Yeah.
Um,
But now there's a scare of this new COVID strain.
yeah. Is it in Sydney or?
Sydney got 2 cases already, possibly
Oh,
3.
right.
Yeah. There were
But they
some
have been
flights which came
vaccinated.
from Africa.
Right. So does it mean that there will be another lockdown or?
No, I hope not.
Yeah.
Yeah, I think they don't know yet whether this new strain is easily to transmit or not. So they are still working it out.
Right.
But they are
Yeah.
asking everybody to take a booster now.
All right. Yeah. So you still can go to campus or public places.
Yeah, you can go
Mm-hmm.
anywhere now, really. And you can
Right.
get the booster shot from your doctor now, actually.
Oh, that's good.
So it's a bit easier.
Mm-hmm. So it also means that Australia is ready to open the border. Right?
Yes, I think the student flights are coming already
Oh, I see.
from December. Yeah,
Mhm.
one of my student who was stuck in India he's coming on the 9th of December.
Oh, yeah, it's good. Yeah, I think my friends from Indonesia will go next year, maybe. Yeah.
Yeah,
Some of the PhD students at UNSW.
yeah, yeah. You know the Chinese student Keith. I don't know whether you remember.
Yeah,
He was there.
yeah.
Yeah,
I know him.
he arrived already in Sydney.
Right. So yeah, he continues his research
Yeah, so he
now.
was
Yeah.
stuck in China for 18 months.
And
Yeah,
what about his study? I mean, uh, yeah, it's like a delay or
yeah. So he will just get an extension because
okay.
when they are away, it becomes like a program leave. So they take a leave and they not count it towards their candidature.
Oh, I see. All right.
Don't forget that paper we were gonna write.
Yeah. I already finished, but I'm still layouting.
Okay.
Yeah. I think yeah, about this supplementary data as well, because I'm
Yeah,
still
that's
searching for
true. That's true.
for the spectra.
Yeah.
So
Do you
yeah.
have them with you or is in the NMR unit?
It's in the NMR unit, and before I left, I already scanned some of the spectra, and I'm now searching for them because
Okay.
because some of the spectra that I had, it's already included in the thesis, and they are I draw some structure on there, so I'm not sure if I can.
Okay.
Um, mhm.
Um, I mean, if you know the numbers, then we can try to find them from the NMR database. Um,
I think I already sent to the I'm not sure the one that we use
OneDrive,
um OneDrive, but it's the oldest. I can't really remember, but yeah, I
okay.
already scanned all the spectra there, and I put all the spectra
Okay.
in that OneDrive. Yeah, I think
Okay.
I'm gonna ask for the password or email, so I can also log into that. Yeah, because yeah, all the spectra were there.
Okay, okay. Or maybe I can try to log into OneDrive, see if I can access the data, and then I can send it to you.
Yeah. Thank you. Yes. Mhm.
All right.
Yeah, but they are the scanned. Yeah, not the one that I took from the, what is called, the,
The spin or flip or whatever it is.
yeah. It's the one that I scanned. So
Okay. All right. I'll check.
right, it's 2:43 now. Do you want to? Shall we start now or?
Yeah, I mean, up to you. If you want to wait a couple more minutes, up to you. But if you want to start, we can.
Right. Yeah, I think we can start now.
Yeah.
So, yeah. All right. Good afternoon, everyone. Good afternoon, Professor Nares, or maybe good evening, Professor Nares. We are very happy to greet all of you in the Visiting Professor Lecture Series. So we are now in the sixth lecture, if I'm not mistaken, and Professor Norris will continue the lectures about the carbonyl compound. So last week we already Professor Norris already delivered some of the reaction of the carbonyl compounds, and now Professor Norris will continue with with other reactions of carbonyl compounds. And for students or participants, if you have any questions about the reaction or about anything you want to know about the chemical reactions, please put your question in the chat, or maybe you can raise your hand at the discussion session. So I would like to invite Professor Norris to deliver your lecture. Please, Professor Norris.
Yeah. You want to record the lecture video? I don't know
Oh
if that.
yeah,
Maybe.
okay. Thank you.
No
Thank
worries.
you. Yeah. Okay. Yeah, I'm sorry. It's like a lot of agenda that I
Yeah. No
have
worries.
to do this afternoon. All right. Please, Professor Nares.
Okay. Thank you. Thank you for the introduction video. I'm just going to share my screen so that you can see my slides. And you can see my slides, okay?
Yeah.
All right. I'll just make it a full screen. And then I will just get a pen. Yep. And I can use it. Good. Okay. So today we're going to continue with the theme of reactions of carbonyl compounds. You may recall that in the last lecture last week, we learned about carbonyl group, and we learned about the polarity of the carbonyl group, that how carbonyl group can undergo lots of different reactions. Particularly, we looked at nucleophilic addition reactions, because we learned in the last lecture that a carbonyl group is highly reactive. And this reactivity arises because of the C double bond O group, which we have in the carbonyl compound. And we also learned that these can be aldehydes, these can be ketones, and these can be esters or acids. And the polarity of the carbonyl group is you always have a slightly positive end here, and you have a slightly negative charge on the oxygen. So that means nucleophiles which have negative charge or they have electron pair, they will come and attack onto that carbonyl group, resulting in a nucleophilic addition reaction. And we looked at the reactions of Grignard reagents in the last lecture, where we had R, Mg, X, which represents the Grignard reagent. And we learned that R is our nucleophile in this case, and the carbonyl compound reacts with the Grignard reagent very, very readily. And these are examples of strong nucleophiles. So we also learned the reaction of hydride, how that can react with aldehyde or the ketones. And towards the end, we learned about reactions of the amines, which don't have any charge per se, but they have this pair of electrons on nitrogen, and that can react with your carbonyl compound as well. And we learned that the reaction of a carbonyl compound with an amine gives what we call an imine. So if you react that aldehyde, which we have, with a corresponding C double bond O with an amine, you will get a corresponding imine formation, C double bond N, hydrogen, say if we have started with an aldehyde, and R group here, like that. So you get the formation of an imine. So this type of compounds are called as imines. We learned that in the last lecture. Aldehydes, ketones react with amines to give us imines. Another extension of imine is that if your amine has a hydroxyl group attached to it, we call that amines as hydroxyl amine. And the name is quite obvious because there's hydroxyl group, there's amine, and it reacts with the carbonyl group exactly the same way as the amines do. It forms a C double bond N bond, and the resulting product will have a hydroxyl attached to the nitrogen because the starting hydroxylamine has a hydroxyl. So these kinds of compounds are called as oximes. And also if you have NH2, NH, CONH2, and that can also react with a carbonyl group. And the NH2 here will react exactly the same way like an amine does. It doesn't matter what is the rest of the molecule, that's insignificant. What happens is this amine will react to give you a semicarbazone in this case. So this is called as a semicarbazide, and this is called as a semicarbazone. If this was just NH2 compound instead of that, so if your starting compound was just an diamine like that, NH2, this is called as hydrazine. That's a very common chemical which is used in chemistry. Hydrazine, HYDRAZINE, hydrazine. And when the hydrazine reacts with your carbonyl compound, you will get the corresponding compound, which we call hydrazone. So you get C double bond N NH2. So you will get this type of compound, and this type of compound is called as a hydrazone. You started with the hydrazine and you will get a hydrazone. And the same thing is here. The NH2 is called semicarbazide, and this is a semicarbazone. The question you might ask is that why only this NH2 reacts with a carbonyl group? Why not this NH2 on this side over here? There's a reason for it. So typically, when I'm in the class, I will ask the students to tell me why only the NH2 on the other side is reacting. There is a difference in the reactivity between this NH2 and this NH2. This NH2 is like an amide, so it's not an amine, and only amines will react with carbonyl group to form a C double bond N, not an amide, because the amide NH2 is neutral. It's not basic. Well, the NH2 here is basic. So we can talk about this later if you don't understand the concept why this is not reacting and only this is reacting a bit later. Another reaction which is used quite a lot in experimental chemistry in second year is that if somebody gave you a compound and asked you to verify that it is a carbonyl compound, what test can you do to quickly check if the compound you're given is a aldehyde or a ketone compound? So what we do in second year chemistry is that we just dissolve this compound in a bit of solution or a solvent, and then we add to that a reagent which is called as dinitrophenylhydrazine. The name dinitro comes from because it got two nitro groups, and the phenyl is the benzene ring, and NH2 is called as hydrazine, like I was telling you in the last slide. So this reagent is available in a bottle, and you add to your unknown compound, and you just shake it up and warm it up a little bit, and you get the formation of a yellow to orange precipitate. And if you get an orange precipitate, that confirms that the starting compound you have is an aldehyde or a ketone compound, because aldehyde or ketone forms a hydrazone with this hydrazine group which is present in this reagent and give you an orange precipitate. So that's a quick test for presence of aldehydes and ketones. Here is a couple of questions for you. So I got a couple of questions for you here. One is, what product would you obtain from the following reaction? If you have a ketone like this and you react it with hydroxylamine, NH2OH, what would be the product that would be formed? And the second question is, what amine and carbonyl compound are required to prepare this imine? So in this case, the product is given to you, and you are asked what starting materials you will need to prepare these two compounds. So the first question is easy to answer, because we've been learning that whenever you have a carbonyl group, that will react with your NH2 compound to form a C double bond N compound, right? That's what we've been learning. So the answer to this question is going to be very simple. You have a carbonyl, and then you have a double bond over here, and this is going to be your nitrogen, and this is going to be OH attached to it because it's a hydroxylamine, and this side is going to be basically your CH3. So this is going to be the answer to your first question. The second question is, what starting materials I'm going to need to prepare this imine? The easiest way to prepare for this question is that you start breaking that bond, which is the imine bond, C double bond N bond we break. So if you break C double bond N bond, you will realize that we're going to need a carbonyl on the left-hand side where the carbon is, and CH3 is over here. And then you have your hydrogen over here. And on the right-hand side, you're going to need an amine compound. And your amine is NH2. And then you have your CH2, CH2, CH3, which is present on the right-hand side of your molecule. So that doesn't change. That stays the same, CH2 and CH3. So that means these are the two starting materials you're going to need to prepare your product, which is given to you. And this one is exactly the same way. So I'm not going to give you an answer now, but I want you to think about it. And if you don't understand what the starting materials will be from this cleavage over here, we can talk about it during the question time, and I can show you how that product is formed. So that's the answer to the second question. Another reaction we're going to look at now is reaction of the carbonyl compounds with secondary amines. Because at the moment, all the reactions we looked at of the amine were where the amine was a primary amine. By primary amine, we mean that the nitrogen of the amine has two hydrogens attached to it. What if the reaction contains a secondary amine? So by secondary amine, I mean that your amine has NH rather than an NH2, and there's an R group attached here, then there's another attached R group attached here. So instead of nitrogen having two hydrogen atoms in the secondary amine, the nitrogen only has one hydrogen present on it. So what will be the result of the reaction of a secondary amine with an aldehyde or a ketone? The product you will get from this reaction is called as an enamine. Rather than imine, you will get an enamine. An example of an enamine is this structure over here. So the difference between an imine was C double bond N, remember from the last slides? This was an example of an imine. The enamine has a nitrogen over here bonded to a double bond. So there is a double bond over there, and the nitrogen is bonded to it. So that type of compounds are called as enamines. And enamines are also formed by the addition of nitrogen nucleophile followed by elimination of water. So we also learned in the case of enamines that the imines, they are also formed by the nucleophilic attack of the nitrogen followed by elimination of water. That's what gave us imines. However, when you have secondary amines rather than primary amines, elimination occurs across two adjacent carbons. What do we mean by that? I'll show you that in a minute. So that means instead of losing water from this side of the molecule over here, you lose that hydrogen which is present on the adjacent carbon. The reason is that this carbon over here doesn't have any hydrogen attached to it. So that means we can't lose water from this particular carbon because there's no hydrogen attached here. So you can lose a hydrogen from the other side to give you the corresponding enamine compound. And we'll talk about that in a bit more detail when we come to the mechanism. So what happens in the reaction with the secondary amine? The first step is what we call is an addition reaction. Just like an amine reacting with a carbonyl compound, this secondary amine nitrogen reacts with that carbonyl compound to give you an intermediate which is very similar to the intermediate we got for the primary amine when that was reacting, right? And then similarly, you get a transfer of a proton from this proton to that oxygen. That nitrogen proton goes to the oxygen to give you an amino alcohol. This is what happened in the case of primary amine attacking the carbonyl as well. The first step was the formation of the amino alcohol, exactly the same way. There's no difference. And then the third step or mini step is also similar. A trace acid catalyst protonates that hydroxyl. And you can imagine that the water can be lost by using that pair of electrons which we have on that nitrogen coming around and water getting lost from the reaction. So we got a product which is very similar to the product we got from reacting the primary amine with the carbonyl compound, and also the secondary amine reacting with the carbonyl compound. So there is no difference between the first set of reaction, okay? If this was a primary amine, then we will just get the corresponding imine compound where there'll be no hydrogen here. But because there is no hydrogen present over there, you just got two carbon groups present on the nitrogen, you get this imine compound which has a positive charge on the nitrogen. And that's not a happy situation. So what happens is the adjacent carbon participates. The adjacent carbon has a proton attached to it. So you can lose that proton from the adjacent carbon, giving you what we call this enamine product. So the enamine product is when you got a carbon-carbon double bond and the nitrogen is attached to that carbon over there where the double bond is. And this reaction only happens when you have a secondary amine reacting with a carbonyl compound to give you what we call an enamine product, double bond, and then the nitrogen is attached to the double bond. Okay, this is what we call an enamine compound. Okay, because there is no hydrogen here, because if there was a hydrogen present here, then what will happen is you will lose that hydrogen, which is, say, for example, if this was hydrogen here, the hydrogen will be lost and you will get your standard amine product. But because there is no hydrogen present on this nitrogen, you get this intermediate over here, and the neighboring group then gives away a proton to form what we call an enamine structure. So this is the structure of the enamine compound, and that's the basic difference between the reaction of a primary amine with a carbonyl compound versus the secondary amine with a carbonyl compound. One give you enamine and the other give you a imine. Okay, so remember that. And let's just look at a couple of examples. If you react this carbonyl compound, which is a ketone compound, with the secondary amine, which is the dimethylamine, you will find the product you will get will be the corresponding enamine compound. The intermediate in this compound obviously is going to be a compound which is going to be C double bond nitrogen, and then you have a CH3 group here and a CH3 group on the other side, and a CH3 over here with a positive charge. And then the neighboring hydrogen participates from here. Because there was no hydrogen present on this, only one hydrogen present on this amine. So this comes around here, and this goes over here to neutralize the charge, and you get the corresponding enamine compound. And the same thing applies here when the carbonyl reacts with the secondary amine. This is also a secondary amine, except this amine is in a cyclic form. You will get also enamine, the double bond, and then the nitrogen. So the intermediate in this reaction is again corresponding double bond nitrogen with a 5-membered ring over there like that, and the positive charge is over here. And then you can lose a proton from that CH3, the adjacent carbon that comes around here, and that goes over to the nitrogen to give you this product, which we call an enamine product. Okay, that's enough about imines and enamines. One thing to remember about around the imines is that C double bond N can also be reduced or can also react with a hydride reagent to give you the corresponding amine compound. So if you form an imine and you react that with borohydride reagent, the reducing agent, a mild or a strong reducing agent, you can reduce the C double bond N to the corresponding C double bond, C single bond NH compound. Okay, so that's quite easy to do. Okay, we have done enough reactions of amines. So I want you to think about the reactions of the next with water. Instead of amine, we're gonna use water as a corresponding reagent. Okay, instead of amine, we're gonna use water, because water also has lone pair of electrons? Can water or can alcohol? Another example is, what if you take an alcohol? Say the simple alcohol is methanol, CH3OH. So the question is, can an alcohol react with a carbonyl compound? So this is like methanol. Can this react with a carbonyl compound? Can water react with a carbonyl? Or can even hydroxyl OH minus react with a carbonyl compound? So we're gonna ask ourselves, can oxygen be a nucleophile in these reactions? Okay. If you take a carbonyl compound and you react with water, the product you will get will be what we call a hydrate. So you might ask how this hydrate comes about. So you can imagine you have C double bond O R group. This is a ketone. And you're trying to react it with water. And you can imagine that the water lone pair on oxygen will attack that carbonyl group, and you can move that across here. So you can see that this carbon is going to have two oxygens attached to it if water reacts with it. And this type of compounds are called as hydrates. And you can see the equilibrium here. This is an equilibrium reaction. So depending upon the stability of your hydrate, the reaction can either be in the forward direction or in most cases in the backward reaction, because carbonyl compound, when you try to react them with water, they will rather happily stay as carbonyls and not react with water unless there is a special case. However, the reaction goes to completion for highly reactive aldehydes and ketones. If you have a highly reactive aldehyde and a highly reactive ketone, and an example of a highly reactive aldehyde is trichloroacetaldehyde. So this is that the CH3 that is present in acetaldehyde, all the hydrogens are converted to the corresponding corresponding chlorine. So that becomes a trichloroacetaldehyde. So this molecule is called as an acetaldehyde. That's a simple compound. The trichloro, you remove all the hydrogens and put chlorines. And if you react that with water, this carbonyl is so reactive because of the electron attracting chloride present there, that the water can react with the carbonyl group to give you this hydrate compound. It's called chloral hydrate. And the equilibrium here lies to the right-hand side. Or if you take a compound which have three carbonyl groups sitting side by side, and this compound is called as a ninhydrin compound, and the central carbon here is very, very reactive. This can react with water to shift the equilibrium to the right-hand side to give you this stable hydrate compound. So the reaction with water is not favored with carbonyl groups. Only in special cases where you have highly reactive carbonyl compounds, aldehydes or ketones, they can react with water to give you the corresponding hydrate compounds. What about alcohol? Does alcohol react with the carbonyl compounds the same way? Yes, alcohol can add to the carbonyl group, and this is also an equilibrium process. Instead of forming a hydrate, and you may recall from the last slide, the hydrate basically has a hydroxyl group and a hydroxyl group on the other side as well. And if you're reacting with an alcohol, say methanol in this case, OCH3 comes from methanol, you can add one OCH3 onto the carbonyl. And these compounds are relatively unstable. And these unstable compounds are called as hemiacetals or hemiketals. I just have to stop for 1 minute. I want you to think about this a little bit more, and I will come back to that in a second. I just need to look at something urgent. I will just be back in 1 second. Please have a look at this reaction.
Sure. Ya, baik semuanya. Jika ada yang ingin ditanyakan begitu ya, tidak perlu ragu-ragu, kalian bisa menulisnya di chat ataupun nanti bisa berdiskusi langsung begitu dengan Profesor Nares.
Okay, sorry, I'm back.
Yeah. All right.
Yeah, so I want you to think about it, that how this compound could form. This is we calling that a hemiacetal and calling that a ketal. Hemiacetal because it comes from an aldehyde. Aldehyde has this structure, C double bond, oxygen, hydrogen. This is your aldehyde. So if aldehyde reacts with methanol, this is we're taking example of methanol, and methanol has this structure, CH3 OH. This is your methanol, and methanol also have this pair of electrons over here, and this can come and attack this carbonyl group as well, and the result of that is you're going to have a hydroxyl group which is coming from this oxygen, and you have OCH3 which comes from alcohol. And if you start with an aldehyde, this is called as an hemiacetal. And if this is a hydroxy, methoxy, and a ketone, is the starting compound here is a ketone, which is C double bond O like this. Oops. It's like a ketone, C double bond O. Then it is called as a ketal. And it's called a hemiketal because one is hydroxyl and one is methoxy. If they were both hydroxy, we call them a hydrate. If one is hydroxy and one is methoxy, we call that a hemiacetal if you start with aldehyde, a hemiketal if you start with the ketone. So the definition of a hemiacetal or a ketal is that the hydroxyl group and the alkoxy group, this is, we're calling that a methoxy group. It can be any OR group, it can be any oxygen carbon group. That's why it says alkoxy, and bonded to the same carbon. And the alcohol can also react further with these hemiacetals and hemiketals, where you can remove that hydroxyl also and put another OCH3 group. If both of these groups becomes OCH3 groups, we call them acetals or ketals. Instead of calling them hemiacetal and hemiketal, we call them acetal or ketal. And we'll see that in a minute. In general, the addition product from the addition of alcohol is unstable. So these hemiacetals or hemiketals, they are unstable. Just like the carbonyl hydrates we saw. When you had 2-hydroxyl, the compound was unstable. When you have hemiacetal or hemiketal, these are also unstable. Typically, they cannot be isolated. So if you do a reaction of a carbonyl compound and you want to isolate this intermediate hemiacetal or hemiketal, you will find that it's hard to isolate them. They are unstable. But there are exceptions to this rule. The exception to this rule is that if you have the hydroxyl group and the carbonyl group present in the same molecule. In the last slide, we saw alcohol is here, ketone is here. What if we somehow link that carbonyl compound with the alcohol compound? What if we join them together? They're present in the same molecule. Will that make them more stable? So the exception is when the hydroxyl group and the carbonyl group are present in one molecule, you can stabilize these hemiacetals. Otherwise, they are unstable. And also, if they can form a 5-membered or a 6-membered ring, then that's also stability that comes to the molecule. So that means in those cases, the cyclic hemiacetals, they will be more stable and they can be isolated. So generally, when you have hydrates or hemiacetals, you will find that they are unstable. The equilibrium lies towards the ketone, starting aldehyde and ketone. So they hydrolyze off very quickly and go back to their starting compound. But if you have the hydroxyl and the carbonyl present in the same molecule, we will see the example in a minute, then they become stable. And if they can form a 5-membered or a 6-membered ring, that's even better. Then they can be stable, they can be isolated, and the equilibrium lies towards them. Here's an example of cyclic hemiacetals. This is your aldehyde, C double bond OH. It is present in the same molecule where an alcohol is present. So this compound basically has a structure where you have OH, CH2OH, and the COH aldehyde present in the same molecule. There is no bond between these hydrogens, so excuse me. There is no bond there, they're just present in the same molecule. So if you want to write it in a linear fashion, you can say that this compound is basically 3 CH2s and the aldehyde. I'm just going to put 3 in the bracket here because it's easier to draw. 3 and aldehyde, C double bond OH, this structure. This is the structure we are talking about, okay? So it's not cyclic structure, it's just a linear structure, but the aldehyde and the hydroxyl are present in the same molecule. In this case, the equilibrium lies towards the right-hand side because it satisfies 2 criteria. One is the hydroxyl and the carbonyl should be present in the same molecule, which it does. I tick that box. And also it should form a 5-membered or a 6-membered ring. It's forming a 5-membered ring. So that ticks the box. So that means this is going to be more stable. And a classical example of a cyclic hemiacetal, which is really stable, is glucose. That's the glucose we take as a source of energy. Glucose lies greater than 99% in the cyclic form, cyclic hemiacetal form, rather than the corresponding aldehyde open chain form. Only 0.003% is present as the aldehyde. Does this satisfy the criteria? It has the hydroxyl group and the aldehyde present in the same molecule, and it forms a 6-membered ring. If you count 1, 2, 3, 4, 5, 6-membered ring. So it meets the 6-membered ring criteria. It also meets the alcohol and the aldehyde present in the same molecule. So cyclic compound is favored in these cases. Otherwise, hemiacetals are quite unstable compounds. Now, as I was telling you, that the hemiacetals that are formed by the reaction of a carbonyl compound with an alcohol can react further. And if you react them further, the second alcohol here can also be removed with an OCH3 group. And this type of compound is called as a acetal or a ketal. If you start with an aldehyde, then it'll be an acetal. If you start with a ketone, for example, we started with a ketone here, the product will be a ketal if you start with a ketone. So if you start with a ketone, you will get ketal. If you start with an aldehyde, you will get an acetyl. And these structures here, they are stable structures. Hemiacetals, hydrates, they're unstable. But once you get the corresponding acetals or ketals, they are stable structures. Okay, it's basically very easy to do. You take your carbonyl compound, you add alcohol. This alcohol can be in excess, and you can add an acid catalyst, and the reaction will go all the way to this compound over here, shown in this manner. And this type of compound is acetal or ketal. And these acetals and ketals are quite useful compounds in organic chemistry. But let's just look at a few examples. If you take an aldehyde like this, reacted with excess alcohol in the presence of acid catalyst, you will replace that double bond with the carbon single bond oxygen, CH2, CH3 on this side, CH2, CH3 on this side, and you will have your corresponding, in this case, an acetal compound. You can start with an aldehyde. This is your acetal. It can be a cyclic ketones. If you start with a cyclic ketone over here, then this carbonyl that is present will react with alcohol to give you a ketal product. So this is like a cyclic ketal product. You can also take a ketone or aldehyde and react with the diol, because you may remember that this is a two-step process. You get reaction with one alcohol to give you that, where you got OH and OCH3. And the second reaction is where the OH is replaced by the second OCH3 group. If you start with the diol like this, you will react it once. So the first product in this reaction, if I just draw the first part, will be oxygen with an OH, and you will have a oxygen, and you will have a CH2, 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 and an OH, because this is a cyclic alcohol we are dealing with, and you will get that intermediate formed first, and this will react with itself to give you the corresponding cyclic ketal in this case, because starting with ketone. So if you start with a mono alcohol, you will just get two of the same, adding two of the same. But if you have a diol where there are two alcohol present in the same molecule, then you will get a cyclic structure like that, which is also an example of a ketal or acetal if you start with an aldehyde. Also, another thing to remember is that the reaction to form an acetal or ketal is a reversible reaction. So this reaction is a reversible reaction in the sense that you can see this is all reversible reaction. So that means from here, we can also go back if we want to get our aldehyde or the ketone back. So the reaction is actually an equilibrium. An excess alcohol and a trace of acid or some means of removing water leads to high yields of acetal and ketal. But if you do the reverse reaction, where you add lots of water, where there's lots of water present, like aqueous acid, for example, you will get the reverse reaction where you will regenerate the carbonyl compound or the carbonyl group that is present in the molecule. So an excess amount of water in the presence of acid catalyst will convert this acetal and ketal back to the aldehyde or the ketone compound. So this reaction is very useful. We use that as a protecting group in organic chemistry. If you want to somehow protect your carbonyl compound, you convert that to an acetal, and then you do whatever you want to do with your molecule. And later on, you treat it with water in the presence of acid, you will get your aldehyde back. And I'll show you an application of this reaction on the next slide. That is how acetals can be very useful in organic synthesis. You got this molecule here. This molecule has a carbonyl group as well as a double bond. If you want to convert this compound into a compound where you don't want to reduce your carbonyl C double bond O, you only want to reduce the double bond. So we want to go from this compound to this compound, but we don't want this group to be reduced, because all reducing agents will, to some extent, will react with the carbonyl group as well as the double bond. But what we want to do is we don't want to lose this carbonyl group that we have. Because what happens is, if you try to reduce this compound, you might also get compound where the carbonyl might also get reduced. So you might end up with this molecule here, which we don't want. What we want to do is we want to only specifically reduce this double bond. So what we can do is we treat that with methanol and acid, and we convert that carbonyl into a ketal compound. So we put OCH3, excess methanol, bit of acid, and then we do hydrogenation. We reduce that double bond to a single bond. And after we've done that, we treat it with excess water in the presence of acid catalyst that will convert our ketal back to the carbonyl compound. Okay, so it's like protecting your carbonyl, doing a reaction, and then regenerating your carbonyl group. We call that protective group chemistry. Or you can mask or you can protect your carbonyl compound and then regenerate it when the reaction is done. And that's what we call a protecting group. And acetal and ketals are examples of what we call protecting groups. Now I got a reaction for you. What we want to do is we want to react this compound with this compound to form this compound. So this is our target compound. We want to make this compound. And if we think about it, we can say, we can make this compound by a Grignard reagent. We can make this Grignard reagent, and then the carbon here will attack our aldehyde compound, and we will form the corresponding alcohol compound. That's the first thing comes to mind, that if you want to make that compound, we do a Grignard reaction, and we know that the Grignard reaction will give us the alcohol, and we will attack that via this kind of compound. So we convert that CH2Br into CH2 magnesium, and then the CH2 will attack the carbonyl to give us this compound. But there's a problem. The problem is we cannot generate this Grignard reagent because it has an aldehyde. Because this Grignard here will react with itself. You can imagine that if there's another equivalent of Grignard reagent formed, it will react with itself. So you have a CH2, CH2, CH2 aldehyde. And what will happen is that it will attack itself readily and destroy itself. So you will get a polymeric mess. So this compound, Grignard here, cannot be generated in the presence of aldehyde because the aldehyde will start to react with itself. So one way to get around this problem is that you can protect, you can hide this carbonyl group here. And one way to hide is that you form an acetal. So this is an example of an acetal because it starts with an aldehyde, and aldehyde gives you the acetal compound, right? Aldehyde react with an alcohol in the presence of acid to form an alcohol acetal compound. And now if you form Grignard reagent, magnesium bromide, this will happily form the magnesium bromide reagent because there is no aldehyde present to react with itself. This can then react with your aldehyde compound you want to react it with. So this can now attack your aldehyde starting material and give you this protected product. And we can regenerate our aldehyde from this acetal by simply treating it with water and acid. So these acetals and ketals are very useful protecting group. They can hide, they can mask your carbonyl group, and then you can regenerate that carbonyl group later after your reaction is done. So that's where the usefulness of these acetals come into play. Now, I want you to think about this reaction here. What I want from you is show me the structures of the alcohol and the aldehyde or ketones you will use to make the following acetals. So we're given two compounds. One is a ketal. So this is a ketal compound. And the second one is a acetal compound. And we are asking you what starting materials you will need to make the following. It should be acetal and ketal, following acetals and ketals. You know what I mean here, because this is a ketal and this is an acetal, because one from aldehyde and one is from ketone. So the question is, how would you get these compounds? So I want you to think about it for a couple of minutes, and we can then talk about that. And if you have any questions so far on this section, we can also answer the question. So I want you to have a think about it for a couple of minutes, and we will take a break for 2 or 3 minutes. And I want you to write the answers for these two, and then we'll look at the answers in a couple of minutes. So let's just have a break for a couple of minutes. And then in the meantime, I want you to think about the answers, and then we discuss the answers in a minute.
Sure. Thank you, Professor Norris. So everyone, if you know the answer of these two questions, you can write the answers in the chat room. Jadi kalau misalkan sudah tahu nih kira-kira senyawa karbonilnya yang mana, kemudian alkoholnya yang mana, begitu ya, bisa dituliskan di chat. Nah, bisa dituliskan nama senyawanya, nama alkoholnya apa, begitu. Atau kalau misalkan nanti ada pertanyaan, bisa langsung disampaikan begitu atau ditulis di chat. Boleh menggunakan bahasa Inggris, boleh menggunakan bahasa Indonesia. Nanti saya bisa bisa bantu untuk translatekan kalau misalkan ragu-ragu begitu ya. Nih, jadi walaupun strukturnya mungkin terlihat menjelimet gitu ya, atau rumit, nah, tapi kita harus tahu nih inti dari reaksi ini dia melibatkan senyawa apa dan apa gitu. Dan ini kita masih berbicara di sini sudah disebutkan strukturnya alkohol dan aldehid atau keton apa yang digunakan gitu ya. So which carbonyl or alcohol compounds that you would use for this product.
Okay, how did we go? I think everybody probably got the answer.
Yeah.
Sorry?
And maybe some of the students are too worried if they answer are right or not.
Oh, don't worry about that part. I think the best way is to try it and
Yeah.
suggest an answer. If it's correct answer is good. If it's not, then we can think about it why it is not the right answer. But
Mhm, mhm.
all answers are good.
Yeah.
All right, so let me actually help you with guys with that. So I'm just trying to draw the 5-membered ring. It's a bit hard to draw with a mouse. Oh, sorry, it doesn't look like a 5-membered ring at all. I'll try again. It's just that with a pad, it's hard to draw with this. So, oops. So this is a 5-membered ring, and the carbonyl you're gonna need is this ketone over here. And since you got a cyclic compound, so you can simply draw that as OH, just like the one shown in that structure is just gonna be come on pen, just gonna be that. Just these are the two things you're gonna need. And when you do this reaction, you always need an acid catalyst a little bit, so there's going to be acid catalyst present as well. And this one is easy, it's just alcohol. So that means you're going to need excess amount of alcohol. So you're going to need OH, CH2, and CH3. This is like a solvent as well as a reagent, so you can use that in excess. And the corresponding aldehyde compound you're going to need is where you have a benzene ring, just like that. And then you're going to have your C double bond O hydrogen present as an aldehyde. Okay, so you're going to need excess amount of that aldehyde and a trace amount of acid that will give you the corresponding acetal compound. Are there any questions so far up to this section? You can ask me now, or you can ask at the end when we finish reactions.
So yeah, please students, if you have any questions, you can write them in the chat or maybe discuss directly with Professor Nares. Honestly, I have some questions, Prof, but yeah, maybe later I will ask.
Okay, let's do it at the end. Okay. Yeah. The next reaction we're going to talk about carbonyl groups is becoming to the end of nearly the reactions of the aldehydes and ketones, is what we call a Wittig reaction. So a Wittig reaction converts a C double bond O into a C double bond, into a C double bond C. This is what we call a Wittig reaction, conversion of a carbonyl to an alkene. This reaction, Wittig reaction, was discovered in the laboratories of this scientist here, George Wittig. And you will be surprised that he got the Nobel Prize for Chemistry in 1979 for the discovery of this reaction. So it's the carbonyl addition that produces an alkene, okay? But the conversion of the carbonyl to the alkene involves a couple of steps. The very first reaction, which happens in this alkene formation, is the formation of this reagent here, triphenylphosphine reagent, or triphenylphosphonium reagent in this case. And this reagent can be formed quite easily by reacting a compound we call triphenylphosphine. So this reagent is quite common and popular in chemistry. So you can have a phosphorus attached, where you have 3 phenyl groups attached to the phosphorus atom. And this compound is called as triphenylphosphine. It can be written like this, or it can be written like this. The phosphine here reacts with an alkyl halide. While alkyl halide, we mean this is CH3 iodide, chloride, bromide, typically, even so it's mainly chloride and bromide and iodide. It can react to form this phosphonium halide. So this compound is called as phosphonium halide, where phosphor is positive attached CH3. Because there is a positive charge on this phosphorus, a proton from this CH3 group can be removed. The reason why the proton can be removed is there's a positive charge on the phosphorus. So you want to neutralize this charge somehow. One way to neutralize is if you remove that hydrogen from the CH3 to form a negative charge here. This will then neutralize that positive charge you have on phosphorus. And this can exist as P double bond CH2 or P plus CH2 minus, which is resonance stabilized like this. And this kind of compounds is called as a yelide, Y-L-I-D-E, yelide. And it basically contain opposite charges on adjacent atoms. You have a phosphorus positive and a carbon negative. And you may remember that carbon negative is an example of like Grignard reagent, where we saw that the Grignard reagent reacts with the carbonyl compounds quite readily. Here, the reagent is phosphorus attached to a carbon. And the question you ask is, how do we remove a proton from a CH3, which is next to phosphorus? And that is done by using a quite strong base. And that strong base is called as butyl lithium. So this is a very, very strong base. And this reagent is also very, very reactive and pyrophoric. Pyrophoric means it can catch fire very easily, but it's a very strong base. And it can remove a proton from that CH3 to give us this yelide, which we want. Okay, so the Wittig reaction involves first reacting an alkyl halide with a phosphine compound to form a phosphonium compound. And then from the phosphonium compound, we remove a proton from the carbon that is present adjacent to the phosphorus to give us what we call a yelide. And this yelide then reacts with your carbonyl compound. Just like the Grignard reagent, the CH2 minus attacks that carbonyl, and then oxygen forms a bond with phosphorus. CH2 minus attacks that carbonyl. In the Grignard reaction, this becomes O minus and becomes OH. But because there's a phosphorus positive present next to it, it forms a four-membered ring. CH2 attacks carbon, oxygen attacks phosphorus, give you this intermediate structure. And this structure here doesn't want to hang around because it's a four-membered ring, and four-membered rings are not particularly stable. And this breaks apart. It breaks that phosphorus-carbon bond, and it breaks that carbon-oxygen bond to give you your alkene. So C double bond O has become C double bond C, and the phosphine is lost as a phosphine oxide, P double bond O. It is lost as that. And this reaction is really, really useful reaction to make alkene compounds. And it is also completely regioselective. That means the carbon will attack CH2 minus, will attack the carbonyl, phosphorus will join with oxygen, and it'll break in this manner to give you the corresponding alkene compound. That's why the person who discovered this reaction got a Nobel Prize, because it's such a useful reaction that you can convert a carbonyl to the corresponding alkene compound. This doesn't have to be a CH3. This compound here doesn't have to be a CH3X. It can be any alkyl halide. And whatever substituent is present on that carbon will end up on your product. Here are a couple of examples of Wittig reaction. You have an aldehyde reacting with this yllid, triphenylphosphine. Sorry, it should be PPH 3 like that, or you want to call it either way, it doesn't matter. Just showing that there are 3 phenyl groups present on that phosphorus. This is your yllid. This behaves as if phosphorus is positive and your CH2 is minus. And that CH2 can then attack your carbonyl to give you that 4-membered ring, and then it forms that double bond CH2 compound. So whatever is here adjacent to the phosphorus is going to end up in your product. Oxygen is gone, and that group attaches itself over there. The same thing here. If you have this phosphine, this looks like to be P, single bond, CH3, the resonance structure of that, CH3, and a CH3 over here, right? And this is your plus, and this is your minus. And I was telling you, whatever is present adjacent to the phosphorus group is going to end up in your product. So we're replacing that carbonyl oxygen with a double bond C, CH3, CH3. So basically C double bond O is converted to the corresponding alkene compound. So that means we can use any alkyl halide, generate this phosphonium yllid, and then we can get the corresponding alkene formed in this reaction. The final slide for the day, the final slide for the carbonyl aldehydes and the ketones is that we can also reduce this carbonyl group directly into a CH2 group. That means we can convert C double bond O to the corresponding, we can convert that to a CH2 group. That means we can totally reduce that carbonyl to get a CH2. And that can be done using 2 special conditions. One is called as a Wolff-Kishner reduction, and the second one is called as a Clemenson's reduction. One occurs under strongly basic conditions. The other one occurs under strongly acidic conditions. The Wolff-Kishner reduction requires hydrazine, potassium hydroxide, and a very high boiling solvent, 200 degrees Celsius, quite hot. That will change the C double bond O into CH2. And if you use an amalgam, when you combine a metal with mercury, it becomes an amalgam. When you take zinc amalgam, treated with HCl, reasonable temperature, you can convert the C double bond O into CH2 compound. So the carbonyl group can be reduced to the corresponding CH2 group. That's the message I want to give. There is a mechanism for it as well. And that mechanism is quite advanced for first year level. So I wouldn't go into the mechanism of that. So this finishes the reactions of aldehydes and ketones. Next, we're going to look at reactions of carboxylic acids and their derivatives. But before I do that, I want to ask any questions, or I want you to ask me questions. Otherwise, I'll start asking questions you have in terms of this section so far. So if you have any questions, now is a good time to discuss the questions for aldehydes and ketones. There's nothing in the chat at the moment. So if anybody has any questions about aldehydes and ketones, any from the beginning to now, I can discuss that with you.
Yeah, thank you, Professor Nares. I think especially for the carbonyl compounds, maybe some of the students are confused which reaction it is, and because we know that a lot of reaction can happen onto the carbonyl compounds. Maybe, yeah, because I always find that some students feel confused, yeah, really confused about
Yes.
what should I do with this reaction if they are given reactants, they are given a nucleophile and then the carbonyl compounds, and then what kind of reaction it is.
Yes.
All right. It is, as Professor Nora said, it is the perfect time to discuss about the, especially the reactions of the carbonyl compounds.
Don't be
Yeah,
shy about asking questions. Just
yeah,
feel free to ask anything.
yeah. Please, Professor Nores, allow me to speak in bahasa. Baik, adik-adik semuanya, mahasiswa semuanya, jika ada pertanyaan boleh disampaikan. Di sini saya melihat, ada Ibu Gebi. Terima kasih Ibu Gebi sudah hadir. Kemudian ada mahasiswa saya ini, ada Melinda, Ai ada. Kemudian saya juga lihat ada Budi Arifin. Selamat sore Ibu Gebi.
Sore Bu Fi, terima kasih.
Iya Ibu. Yeah, Professor Nares, yeah, she's Ibu Gebi, one of our organic lecturer as well in our department.
Yeah.
Yeah, hi Budi. I would like to greet Budi because Budi is one of the participants who joined with us since last week. I also saw you, Budi. Yeah, maybe if you have any question.
Okay, thank you.
Okay.
Hello.
Yeah, we can hear you.
Thank you, Professor Kumar. Thank you for your nice lecture. I joined you since the first one when you start about Lipinski rule, etc., and drug stability. Okay. For about the carbonyl group, maybe my question is regarding the amine and enamine.
Yeah.
The first one in the question. Okay. Is there any possibility if we have a primary amine, but when it reacts to carbonyl compounds, the products is an enamine, not an amine?
That's a very good question.
Yes,
I'll just take it back to. So the question was that if we have an enamine, can we get an enamine with a primary amine?
Yes, that's it.
So this is a typical amine reaction. So the question was that if we say, for example, had a CH2 and a CH3, I can put here as well, and this was a ketone, for example, and we had a C double bond O, a CH3. Can we get an enamine from this with a primary amine? So if we say reacted with RNH2, we will get C double bond nitrogen R. Say if we used RNH2 and we have a CH3, and we can have CH2, CH3 on this side. So the question was, can we have, instead of that, an enamine? We lose a hydrogen, say, from this side, so that we form a double bond NR. So there's a single bond between the carbon and the nitrogen, but there's a double bond here, and we have a CH3 over here. and then we have a CH3 over here, so that we now formed an enamine rather than an imine. In the case of primary amines, typically you will get an imine. But if a further cyclization reaction is possible, then it can form an enamine and react further to give you the cyclic compound. Especially if you look at cyclization reactions involving synthesis of pyrroles, the 5-membered ring nitrogen heterocycles, you will find that in some of those cases, the imine that is formed converts to an enamine, and then the enamine cyclizes with a carbonyl. So if I had, say, for example, a situation where I have the double bond, again, the same compound I'm going to draw, if this is NR, and there's a methyl here. I just draw the methyl as well. Sorry, the pen is a bit slow. And then I have a CH2, and I have another carbonyl group present down here in the molecule. Then this amine can react with this carbonyl over here. So you get 1, 2, 3, 4, 5-membered ring. You will form a fully aromatic pyrrole ring system. So in those cases, the imine can also convert to enamine and then cyclizes, because the driving force for that reaction is you're going to get a fully aromatic. So the product from this reaction, this continues, will be a pyrrole, where you will get a 5-membered ring system where you have N. There's an R group present on the nitrogen, and then you have a double bond here and a double bond here, and you have an R over here, and you have your CH3 over here. So you will get a fully aromatic pyrrole ring. So if the reaction has this possibility that after forming the imine, it goes to enamine and cyclizes to give you a fully aromatic system, then it is possible. But in normal circumstances, if you react an aldehyde or a ketone with a primary amine, you will get imine. And you can isolate that imine quite easily. But if there's another group present in your molecule which can react by forming enamine, and there's a driving force for it, then that can continue to give you the enamine and then the final product. Does that answer the question?
Oh yes, thank you, sir. So, it's so clear. It's clear, very clear to me. Thank you for the explanation.
Okay.
All right, thank you, Budi. Apparently, Budi is also one of the lecturer, right? From the IPB University.
Okay.
Nice to meet you.
No, but I still learn too from others, from you, Professor Nares. That's why I join all of your lecture, because we must learn anytime, isn't it?
Yes, that's
Thank
true.
you.
Same with me.
Thank you.
Yeah, it's like never-ending learning.
Yeah.
All right, thank you.
All right. So what I can do now is I can stop this and I can start with the carboxylic acid carbonyl, and then we can do a little bit on that today, and then we can continue with that in the next lecture and finish it sort of halfway through next lecture. Yeah. So I just stop sharing and I share the next set of slides, which is the carboxylic acids and their derivatives and how they behave differently to the I just need to end this. Don't keep, sorry. I just close this window. Record. All right, okay. Now I just share the next screen. Okay, I got it. So now we're gonna use the same theme as carboxylic acids, but as carbonyl compounds. What we're gonna do is look at carboxylic acids and their derivatives. The carbonyl group is the same, but we have this group that is present on the carbonyl. Very first day I told you that when you have an aldehyde or a ketone, in their reactions, the groups that are attached to the carbonyl compound are never lost. The group is always present in your product. When you have, say, a ketone or an aldehyde, and you do reactions of aldehydes and ketones, you will find that this group here, hydrogen, this group here, R, this group here, R, this group here, R, is never lost in the reaction. It always is there in your product. So the hydrogen and the R group cannot be lost in the reactions of aldehydes and ketones. But in the carboxylic acid derivatives, where the group is shown in red, OH, OR dash, OCOR, ClBr, NH2, these groups can be lost in the reaction of the carbonyl compounds in the case of acids and their derivatives. So if you have reaction of an acid, you can lose that OH group. If you reaction of an ester, you can lose that OR dash group. If you have a COCl, you can lose that Cl or Br group. So these are the groups that can be replaced by a nucleophile. In the earlier examples we saw, nucleophile always added to the carbonyl group and gave you the alcohol. But here you have these groups which can be lost in the reaction. If you look at the carboxylic acids, they are not very reactive compound. They are quite sluggish in terms of reactions. So if you take an acid and try to react it with an alcohol, say if I take an acid and I say I want to react it with an alcohol, say CH3OH, you will find that the reaction is very sluggish. So I want to react this acid, say for example, with the alcohol, and I'm wanting to get this product, which will be R C11O in this reaction, O CH3. I want to get this acid to react with the alcohol to get this product called ester. I'll find that this reaction is very sluggish. It takes a lot of time and effort to react an acid with an alcohol. But you can convert the carboxylic acids into the activated forms, and these activated forms are what we call acid halides, COCl or COBr. So you can convert this OH group here into a Cl or a Br. And once you convert the acid to a COCl or COBr, these compounds are highly, highly reactive. They can react very easily with alcohols, very easily with amines, to give you all sorts of compounds. So that means you can lose that group that is present adjacent to the carbonyl. And to do that, we convert that to a better leaving group, and that group leaves very quickly, and you get the product. So the carboxylic acids by themselves are much less reactive, but you can activate them to the activated forms. And this can simply be done by taking the carboxylic acid and reacting it with this reagent here, or this reagent here. So this reagent is called as thionyl chloride in chemistry, THIONYL, thionyl chloride. And this reagent is a liquid reagent. So it's a fuming fuming liquid is quite potent. It's has HCl that's coming out of it most of the time. So you take this reagent and you heat it together, you get the product plus a gas. Sulfur dioxide is a gas, so you form a gas. And HCl is also a gas. So that means when you heat these things together, you only get product and you can remove the excess reagent that is present in your reaction. So you can convert quite cleanly an acid into an acid chloride. So is PCl3 and so is PBr3. Now, how does an alcohol goes into the acid chloride? So the reaction we saw in the last slide was that we converted a carboxylic acid to a corresponding compound, which was RCOCl. Is it a one-step process? How does it go from acid to the Cl so readily? What does that reaction involve? That reaction involves an intermediate compound, which is represented by this structure. When you use thionyl chloride, when you use PCl3 is this reagent, and when is PBr2 is this intermediate. The thionyl chloride, S double bond O Cl2 has this structure. Okay, this is the structure of your thionyl chloride, SOCl2, the reagent we use, SOCl2. And this is the structure. So what happens in the first instance is that this alcohol attacks that sulfur group and moves that pair of electrons over here. And then this comes back and kicks out one of the Cl, and you'll get this compound here, plus the Cl minus formed in that reaction. Maybe I can draw that intermediate for you. So what happens is that becomes R, C double bond O, and then oxygen attacks your sulfur. So you got O, then you got S, you got O minus here, and then you have your Cl and Cl over here. Okay, so this is your sulfur, looks like 5, but it's sulfur. So this O minus comes around this way and it kicks out your Cl minus. So that forms this species here with RCO, oxygen, S double bond O Cl, and the Cl minus. So Cl minus comes and attacks that carbonyl, moving that pair of electrons onto oxygen. This comes around, this bond breaks, and Cl minus leaves as well. So you get Cl minus, SO2, and COCl. And the H that was present from the carboxylic acid here, it forms HCl with that Cl minus. So that's actually how this reaction happens. The carboxylic acid is converted into Cl. It's a very common, very useful, extensively used reaction in organic chemistry because the carboxylic acids are not very reactive compounds. And in order to make them more reactive, you activate them by replacing the OH group with a Cl group or other better leaving groups. The idea is to convert them to a better leaving group. And if it's a better leaving group, then the reaction happens much more readily. Another activated form of carboxylic acid we have is we call them acid anhydrides. And the most common acid anhydride, which is used quite a lot and you might have heard about, is called as an acetic anhydride. So acetic anhydride has this structure. So you got C, oxygen, C double bond O, oxygen, CH3. So this compound is called as an acetic anhydride. And this is formed from acetic acid. So basically you can imagine that if you have two of these acetic acids sitting side by side, so you have an OH and an OH on this side, hydrogen, oxygen, then you have C double bond O, and you have CH3. You have two acids sitting by side, and you will, and you lose water from this reaction in the middle. You will get this structure is called acid anhydride. This is also an example of an activated form of carboxylic acid. And the activated forms of carboxylic acids, they are very reactive. The reason for that is that this group here is like a leaving group, and this group can leave very easily. And when it leaves, that means the reaction can happen very quickly. And these are, they react the same way as acid chlorides does. And we saw the example of acid chloride in the last slide, where they were the activated forms and reacted very easily. In terms of the reactivity of the carbonyl compound that is present in the carboxylic acids or the acids or the acid halides or derivatives of carboxylic acids, the first reaction that happens of that carbonyl is very similar to the reaction we saw in the case of aldehydes and ketones. A nucleophile will come and attack that carbonyl group. So that fact doesn't change at all. So you still have the positive end here, your slight positive charge on the carbonyl carbon, and a slight negative on the oxygen. So that means the reaction of the nucleophiles, as we saw in the case of aldehydes and ketones, happens the same way in the case of the acid derivatives. But there is one big difference between the acids and the aldehydes and the ketones. In the case of carboxylic acid and their derivatives, this group here can be lost in the reaction. While in the case of aldehydes and ketones, where this was a hydrogen or a carbon, this group was retained in the product. But here you see that this group here is gone after the first reaction. You do get a tetrahedral intermediate, exactly the same as aldehydes and ketones. What happens is that this group here can be lost. So there are two different scenarios. When the nucleophile comes and attacks that carbonyl and forms that intermediate, you have two options. One is you can lose this Y group here to give you this addition product, or you can lose this Z nucleophile here and go back to your starting carbonyl compound. So there are two possibilities. So what will happen? Y minus will be removed if it is weaker base than Z minus. If Z minus is a strong nucleophile, strong base, it will stay in the product and Y minus will be kicked out. If it is a much weaker base than Y minus, if Z minus is weaker than Y minus, which is going to be eliminated. So what is being eliminated in this reaction is Y minus. So it depends upon how strong the base Y minus is. If it is a weaker base, then it's going to be expelled. But if Y minus is a stronger base, then it's going to be retained, and Z minus will be removed, and you will get your starting material back. But if they have equal strength, then you will get a mixture. You will get some product and some starting material. So that's the fundamental difference between the reaction between an aldehyde and a ketone versus a carboxylic acid derivative. That in this case, the derivative or the group that is present on your acid derivative can be lost in the reaction, while in the aldehyde and ketones is not. And the removal of this group depends upon how strong is your nucleophile. If nucleophile is a strong base, then Y minus will be eliminated. If Y minus is a strong base, then Z will be eliminated and you go back to the starting material. If they are equal strength, then you will have a mixture of the product and the starting material. If you can understand this bit, then you understand all the reactions of the carboxylic acids and their derivatives without any problem. And this is highlighted here, that if you have an acid chloride, if you have an acid anhydride, if you have an ester, if you have carboxylic acid, if you have amide, these are all derivatives of carboxylic acids. This is the most reactive and this is the least reactive. So this is the order of reactivity of these compounds over here with the substituent attached to the CO functionality. That means Cl here is a very good leaving group, because if you look at this here, Cl minus is a very weak base. If Cl minus is a very weak base, it can be eliminated quite readily in this reaction. And NH2 minus, if you come on the other side, if you lose NH2, you will have NH2 minus. And that's a very strong base. So that means this is going to be least reactive, because you can't simply eliminate the NH2 minus group from this substituent that is present on the carbonyl. So I want you to spend some time on this slide and think about it, and the last slide, and think about it, that which of those groups are going to be the most reactive and why, and which is least reactive and why. If you understand that part, then you understand all the reactions of carboxylic acids and their derivatives. So I want you to spend some time and think about it during today, because tomorrow we have another lecture, and we'll try to finish that in the lecture tomorrow in about next, I don't know, we'll take about half the lecture tomorrow. And then we will move on to alkenes after that. But I want you to think about it and try to understand what is going on in that slide, the last slide and this slide. And if you understand it, then you understood the reactivity of the carboxylic acids. Okay, I think I'm going to stop here today because it's 8:20 already. And I'm happy to answer questions. So feel free to answer questions on anything we have covered so far.
All right, thank you, Professor Nares. So Professor Nares already explained about the reaction of carbonyl compounds with amine, and then water, alcohols, and Professor Nares also introduced us into the carboxylic acid. So everyone, is there any questions? Actually, Prof, I have a question.
Yeah.
So it's still about the reaction of carbonyl compounds with amine when forming enamine. Yep. If we have two possible hydrogen alpha, which hydrogen that will lose, or which hydrogen that will be removed? If those hydrogen alpha unsymmetrical?
That's a very good question. So let me just draw a simple scenario here. So let's say your question was that if we have two possible scenarios. So let's just put a methyl group here for a change. Oops, sorry. Let's put a methyl group over here. And we say that we got this ketone over here, C double bond O. And this is a non-symmetrical ketone. And we reacted with, say, dimethylamine, which is your secondary amine, right? So there's two possible products now in this reaction when we form, when we form the enamine. So I just put CH3, maybe I should call them Me. So the two possible products are, you can get enamine this way, where you form a double bond and say methyl here. I wouldn't draw the methyl, just say methyl here, and you have a CH3 there. And the second product you could get is that you can form the enamine, which is double bond on this side, methyl over here, and then you have your NMe. The intermediate will be the same in both cases. So the intermediate structure, if you want to draw it, it will be basically, you will have a double bond nitrogen, and then you have your methyl here, and a positive charge, and you have your CH3 over here present. Okay, this will be the intermediate compound that is formed. But then you have a possibility of losing hydrogen from this side, or losing hydrogen which is over there, to form two possible products. So if that goes that way and that goes over here, you will get this product. And if this goes that way, sorry, and the other goes there, then you'll get this product, right? So the question is, which one will it form? Will you get a mixture, or will there be one product? The product that will be formed in that reaction will be this product here. Because the substituted enamines, highly substituted enamines, are more stable than less substituted enamines. So this enamine is less substituted because it has a hydrogen as a substituent, while this double bond enamine here has got a carbon group here, which is methyl, and then there's a carbon group here, and nitrogen group here. So this is more substituted. So if there is a two possibilities, always look for which enamine is more substituted at the double bond. The more substituted enamine is, the more stable it is, and that's the one which predominate.
Okay, thank you, Professor Nares. So we have to look at the stability of the enamine. So which one is more stable, so it will form, or is it any possibility for the formation of mixture of both the products?
Normally you don't see a mixture. Normally you see mainly one compound, enamine, which is more stable. Even if the other is formed, it will, it's like an equilibrium situation, so it'll shift to that side.
Sure. Thank you, Professor Nares. All right, everyone, students, do you have any questions? Or today's lecture is already clear to all of you, hopefully. Right. We now at and I think Professor Nares, if you don't mind, I have one more question.
Yep.
Yeah, about the reaction of carbonyl with the alcohol. So it always favors to form the acetal rather than the hemiacetal.
Yeah. Yeah, because hemiacetal is reversible. You can go back to the ketone quite readily. It's an equilibrium reaction. While once you form the acetal or the ketal, they require water, reaction with water to go back. while the hemiacetal and ketal is just basically the intermediate product.
All right. So even if, yeah.
Yeah, sorry, yeah.
Even if the reaction is 1:1 ratio,
Yep.
for example, if we use 1 mole of 1 equivalent of methanol and then we react it with 1 equivalent of aldehyde, it always goes to acetal.
Yeah, no. In order to go to acetal, you will need excess methanol. Because it's like a reversible reaction, and in order to push it forward, it's like a Le Chatelier principle. You have to drive the reaction towards the product somehow. And one way to do it is to add excess methanol or alcohol. On the second way is that you remove water from the reaction, because when it reacts, it forms water. So if you can remove water by azeotropic or using a Dean-Stark apparatus, you can remove water, or by adding molecular sieves, you can drive the reaction forward. But if you use 1:1 equivalent, it's just gonna be a equilibrium mixture. And when you're gonna try to isolate the hemiacetal, it's gonna go back to the ketone aldehyde or ketone compound all the time, unless there is some driving force which is forcing towards the product. Like we talked about having hydroxyl and carbonyl in the same molecule, and also forming a 5-membered or a 6-membered ring, then the equilibrium will shift to the right.
Okay, thank you, Professor Nares. Yeah, so any question from students? Otherwise, we will see you again tomorrow at 2:40 p.m. Bandung time.
Yep.
So yeah, tomorrow Professor Nares will continue with the carboxylic acid. So now tonight, maybe you can prepare the question for Professor Nares tomorrow.
Yes.
All right. If there is no more questions, maybe we can end this lecture. So thank you very much, Professor Nares, for the clear explanation, and hopefully the students can understand what Professor Nares talked about this afternoon. And for students, don't forget to fill out the attendance form, and we will see you again tomorrow at 2:40 p.m. Bandung time. And thank you once again, Professor Nares. See you again tomorrow.
Yep. Okay. You're welcome. Goodbye.
Have a good rest. Have a good night, and thank you very much.
Thank you. Bye.
Thank you. See you. And thank you to all students. Terima kasih untuk semuanya. Terima kasih ada Ibu Amelinda, Ibu Gebi. Terima kasih yang sudah bergabung. Besok kita akan kembali lagi di jam yang sama 2.40 sampai 4.20. Terima kasih. Maaf absen, mohon di-share ulang. Oke. Bagi yang belum mengisi absensi, silakan untuk diisi. Oke. Baik, terima kasih semuanya. Assalamualaikum warahmatullahi wabarakatuh.
Salam.